Welcome to the Artificial Intelligence Podcast with your host, Dr. Tony Huang. Today, we're with a special guest and a returning guest, Hagay. Can you introduce yourself again?
Hey, Tony. Great to be here again with you for the third time. My name is Hagay. I'm the Senior Vice President of AI Inference at Cerebras. At Cerebras, I work with a group of really world-class engineers, researchers, building Cerebras Inference, which is built on top of very strong foundation, the Cerebras wafer scale engine, which I'm sure we'll talk more about, Tony.
Sounds good. So I'm curious, so inferencing just officially overtook training. It's now like 2/3 of all of the AI compute. So like for years, the entire industry obsessed over like who had like the biggest like training cluster. So like how did everyone almost miss that, running models would become such a bigger business than actually building them?
Yeah, you're spot on. Inference is overtaking training as the more larger AI workload out there. It's been kind of coming for years. I think we all, or many of us, expected that to happen. But I think when now that it's happening faster than many of us have thought. The world shifted from kind of models being the interesting part, and frankly, also not too many people were aware of AI back when it was more about building models. It was more about, geeks, researchers, folks in the field. But what's going on today is because AI is being so successful, so, many folks we know who may not be technologists know ChatGPT and even use it on a daily basis. And many coders out there use OpenAI Codex or Cloud Code. What's happening is that this massive adoption that we're seeing is just pushing more and more workloads from training to inference. Now, my view is that training workloads are not going anywhere. They'll still continue being with us. They're going to grow as well because we train larger models and we train them on more data. And we have new modalities beyond text, like image, video, audio. So training workloads will continue growing. But the thing is that inference, the scale of the inference workload is kind of coupled with the adoption of AI. And we're not even scratching the surface of AI adoption. We have, what is it now, 9 billion people on this planet. Majority of them are still not using AI on a regular basis, but it's changing rapidly. And as it scale, inference workloads would grow and they would dwarf training workloads. It's at this point, it's clear that it's just a matter of time.
So once like the industry realized inferencing was like the real battleground, like companies like DeepSeek, they trained like a GPT-4 level model for like $5 million, and it effectively like wiped out $600 billion off of like Nvidia's market cap in a single day, which was like huge. So does that moment prove that like algorithmic efficiency can beat raw compute? Like what does it mean for like the hundreds of billions of dollars being spent on infrastructure right now?
Yeah, it's a good question. I think the DeepSeek moment was both a foundational moment for the industry, but also mostly a misunderstood moment for the industry. It is true that DeepSeek created a lot of innovation around efficiency, but then I think the figure pointed out of $5 million or whatnot was really not counting everything, right? The DeepSeek team had to do to build and train the model. I think it's grossly kind of undercounting the spend. But regardless, I do think efficiency is critical because if you look at the trajectory we've had with AI models, what really made them very successful is scaling them. OpenAI was the first company to realize that by scaling the models, both the model size and the amount of data it's trained on, so really scaling training, they're able to squeeze out higher and higher quality out of the model they've trained. And they actually even published a paper about that. It's called the scaling laws, where they kind of highlight their empirical observations. By the way, later on, Google DeepMind published another paper of another scaling laws where they pointed out a few misses that OpenAI may have oversaw, and they kind of indicated that the original scaling laws were not capturing everything, and you can actually train even better models in smaller sizes, but using more data. So data was playing a much bigger role than initially thought. But regardless, the conclusion was the same. You scale the size and the complexity of the model, you scale the training data, you get higher quality models. There is a myth floating around that I heard of that says, deep learning has hit a wall, scaling laws do not work anymore, where the models are not getting better. That's complete BS. Models have been getting better for the past 10 years, and they're not showing any sign of stopping. It's just that our bar is becoming higher. But the models are getting better, and they're also growing in that purpose throughout that process. So, just going back to your question, does efficiency matter? 100%, because these models are becoming more complex on one hand. So computationally, they're more expensive to serve. On the other hand, we're also seeing much higher demand from the consumers. So we need to serve more of these models. And, if you combine the increased complexity of the models and the increased demand, very quickly we're going to run out of accelerators, right, to run all these models that everyone wants to use. So efficiency in software, efficiency in hardware is our way, is how we engineer our way out of this situation. And that's also what's happening. There's a lot of push on that. You look at stuff like, quantization. We gradually moved from 32 bits per parameter to 16 to 8. Now 4 is kind of how we serve state-of-the-art models. That's one example of efficiency. There is efficiency in the architecture, where we moved from full dense models into a mixture of experts that are more sparse. So at every inference, every forward pass, we don't activate all of the parameters. We use only a small portion of them. And during training, we make sure every expert specializes. That's another good example of efficiency. There are a bunch of other techniques. We can have 10 podcasts only about inference efficiency techniques. Efficiency is important. Now, the best example I like to use is I'm old enough. I don't know if you can see the gray hair, but to remember the days where to run a speech recognition model, you had to run it in a very beefy server in the cloud. And today, these small marvels of engineering here are running speech recognition, like what's called ASR models, automated speech recognition models, on the phone. And they do it pretty well. I do think, in the fullness of time, more and more of the AI workloads will run on edge devices. We're not there yet. It will take us a while to get there, but I think that's what's going to happen. That's another aspect of efficiency.
Now, NVIDIA's CEO, Jensen Huang, was on stage at GTC 2 weeks ago, and he was projecting that there was going to be like $1 trillion in chip orders through 2027. Can you walk us through what's propelling that demand?
Yeah, that was I also saw that message from Jensen. I think he also even broke this down. I think he said 60% will come from hyperscaler, another 30% for enterprises. And so what we're saying is the hyperscalers, AWS, Google Cloud, Azure, Meta, OpenAI, these companies are ahead of many other companies in leveraging AI, and many of them also have really good insight into what's going on in the market. Take, AWS as an example, right? They already serve so many enterprises and developers, and they have really good insight into future roadmaps and what's top of mind for, CTOs and VP of engineering in these companies. And they're seeing the demand coming, and they're building up their capacity. And they understand something really fundamental, these companies specifically. They understand that compute capacity is super critical in order to scale and serve the kind of incoming workloads. So they're working hard to secure capacity to make sure they can serve all this demand. Now, ordering silicon, the chips, that's something, it's not like you go to Amazon.com, you order, you get it the next day. You have to, be in line. You have to get your quotas from, NVIDIA or from Cerebras or from other chip providers. These chip providers themselves need to work with their supply chain, such as TSMC, which is a really important company not too many people are familiar with, but it's kind of a critical shop if you're developing and if you're manufacturing kind of state-of-the-art accelerators. You need to work with TSMC. TSMC has limited capacity. For them to build a fab, it's billions of dollars and about 10 years kind of a process. So ramping up their manufacturing is very slow and expensive. They also have their own supply chain, like ASML, which is a company, again, not too many people are familiar with. It's a Dutch company that is manufacturing probably the world's most sophisticated machine ever built by man. It's a machine that is doing super precise etching, which is a critical part of the silicon manufacturing process. I won't get too much into that, but that's another supply chain. So there's a very complicated supply chain, and all these hyperscalers that are putting orders with NVIDIA, with Cerebras, with other companies, they understand that the demand is coming for the workloads, and they're working to rack up their ability to serve that demand. I would say it's a little bit like there's a kind of a gold rush of sorts where companies are kind of making sure they have enough turf to be relevant and important, and that turf in our case is compute capacity. There are other aspects to it, by the way. We can dive into that as well. That's data center capacity, power. Those are also key constraints beyond just getting the silicon ready.
Right now, I'm kind of seeing like companies like Microsoft, Google, Amazon, Meta. They're all building their own custom inferencing chips. Like for instance, like Google's TPU Ironwood, or Google Shop. So I kind of like know about that. There's like Amazon's Trainium, and what's kind of interesting is that these like custom chips are growing very fast this year compared to like just GPUs. So my question is like, everyone I know at least uses like the CUDA software from NVIDIA. Is that moat still strong right now for NVIDIA, or do you think that like with all these competitors coming in with their custom inferencing chips that it creates a lot of like competition in that space?
I think I'm trying to find the right way to frame this, but I would say CUDA is no moat. NVIDIA has no moat with inference. That's maybe the simplest way to frame this. And let me explain why. Now, CUDA, just to make sure the audience is aware, CUDA is a set of tools, predominantly a compiler that can take C++ code plus some extension and compile it into binaries that can run on NVIDIA hardware. It's kind of compiles to the NVIDIA architecture. And then CUDA is a family. Beyond the compiler, there are different libraries and things like that. But fundamentally, it's a compiler. That compiler makes it fairly easy to take, again, C++ code with their extension and run neural nets efficiently on NVIDIA hardware. The number of people that can program CUDA is extremely limited. It's very sophisticated. It's very precise. You need to know what you're doing. You need access to the hardware to really test stuff. And so I don't think CUDA is really a moat. Now, when you talk about programming against inference, things are much simpler. All you need is a simple API, REST API. Most developers I know use something like the OpenAI API, either SDK or the API standard. And you don't really need to be an expert C++ programmer to call an inference API. You need to be able to write a very simple, REST API invocation in Python or TypeScript or whatever your favorite language is. So definitely you don't need to know CUDA to use that. So CUDA, I don't think is any moat. I work with hundreds of customers of Cerebras Inference. None of them ever asked me for a CUDA API. What they did ask is great models available in a way that is super simple for them to consume. So that's why in inference there is no moat. You can argue, by the way, that in training maybe the situation is a bit different, and I agree that it's different. Although even there, CUDA is not used. PyTorch is used. PyTorch is a Python library built on top of kind of lower level hardware abstractions and libraries like CUDA and like other low level libraries. Cerebras for training, we also support PyTorch. So people, as long as you use PyTorch, they can run training against our chip. But yeah, in inference things are much, much simpler. It's a stateless API that you invoke. You provide the input, typically text or text and an image, and you get the result back, which typically is text. Now, because of that fact exactly, that there is no moat around inference, and it's very easy to consume inference compute in terms of programming against it, extremely simple, like I mentioned, combined with the fact that the demand for inference is growing extremely fast. What we're seeing is alternative hardware really being successful. And Cerebras, we're one such alternative hardware. The main differentiating factor for Cerebras and why we've been, frankly, pretty successful since we launched Cerebras Inference, which is about a year and a half ago, is that we're 10 to 20 times faster than NVIDIA GPUs or GPUs in general. And the reason we're faster, our secret sauce that is not that secret, is our completely different hardware architecture. I actually have this is a chip, a Cerebras chip. It's not really a chip, it's a wafer scale chip. That's a whole wafer. I don't think everyone necessarily, the audience is seeing this, but if you're watching this on YouTube or whatnot, you can actually see this whole rectangle here. That's a single Cerebras chip. We call it the wafer scale engine because it's the size of a whole wafer. One of these marvel of engineering is sitting in a single Cerebras system. And we have two of these systems in a single rack. Now, this thing here packs about 4 trillion transistors, 44 gigabytes of SRAM, and has a massive memory bandwidth. It's about 2500 higher memory bandwidth compared to NVIDIA's latest chip, the Blackwell, the B200. If you look at compute, it's 30 times more compute than a Blackwell. SRAM, like I mentioned, 44 gigabytes of SRAM, that's 350 times more. This is the reason why this thing is 10 to 20 times faster than NVIDIA GPU. Now, just explaining this just a little bit more, anybody can access our inference on our free tier and just observe the speed. But the reason we're able to be so much faster, that hardware advantage, is that inference is not compute bound. Inference is typically memory bound. And that's because typically you need to go to memory, fetch the next layer of parameters, bring them into the compute cores, do the matrix multiply operations, get the output, and then go back and bring the next set of weights, the next layer from memory. So what's happening is that while the compute cores are working, doing the matrix multiplication, what's really slowing down inference is that access to memory. And the models are becoming larger and larger, so the amount of memory is also growing very quickly. And because Cerebras has this large amount of SRAM, which is the fastest form of memory, on the silicon, co-located with the compute cores, our memory bandwidth is super high, again, 2,500 times higher than a Blackwell, and we're able to do the inference so much faster. This is a hardware advantage. It's physics. It's not software, and it's if anything, going back to your question about the moat, I'd say that's a damn good moat to have, and to really protect our position as the world's fastest inference.
By the way, that's a really cool physical demo. Can I get one of those at some point?
Yeah, you can. If you come to the office, I'll get you one.
Okay, sounds good. I'll take up on your offer, man. So like I have another interesting question. NVIDIA's CEO Jensen Huang said this at GTC. So he said like every time inferencing gets cheaper, like the total demand explodes and there's more compute that gets consumed than ever before. And so like agentic AI, for instance, has made it even more extreme. So there's like every time an AI agent reasons or inferences and like the token generation has jumped from like up to like 10,000 times in like 2 years. So is there like a ceiling on the compute demand or is it just gonna like compound forever?
That's a really good question. I'm sure there is ceiling because we live in a finite, right, universe. But I would also say we can actually go back in time and look at the right, what happened with the internet. Again, I'm old enough. I grew up in a world where there was no internet. And when I wanted to learn about a new topic, I would go to the library and find the encyclopedia, for those that know what this word means. And I would look up the topic and I would read. And I would have to keep it in my head to kind of retrieve that information if I needed to. Of course, the internet changed all of that. The internet completely democratized access to information. And these days people are so used to having internet connectivity, like always on connectivity, they actually get anxiety, right, when they run out of battery or they're in a place where there's no connectivity. And people get used to just using that information retrieval, so many different times a day, right? Both for personal lives and for business. Like my kids, if you take away their phone and internet access, they would go nuts. I would probably go nuts as well. I think with AI, we are in the early phases of adopting it, where we're just kind of learning to use assistants. We use them, a couple of times a day. We're using coding agents more and more. But I do think in a couple of years, we're likely to be in a world where each one of us is using dozens of agents for both personal stuff and for work stuff. These agents are just kind of always on, right? They're doing stuff for us, they're reporting progress, we ask them stuff, we adjust them, but they're always on, always working. I think that's a potential really near-term future that we'll have. And I think it's on one hand, it's going to be fantastic because we'll get so much more things done. Our productivity would, be greatly increased. Our personal lives would be much better in many ways. At the same time, I think we'll start getting anxious if for some reason, right, this intelligence as a utility, I don't know how to call it, maybe that's one way to call it, would not be available for whatever reason. Going back to your question, this would, imagine each one of us, like, majority of the population on this planet having dozens of agents doing stuff for us always on agents. They don't even wait for us to invoke them. They're just running around doing stuff for us. That's going to be, in terms of number of tokens or the amount of processing, multiple orders of magnitude more than what we're using today. So that's why I go back to my statement from earlier where I'm saying, hey, we're just scratching the surface of where inference is going to be. That's one of the reasons that's kind of how I feel about this. And I think the amount of opportunities for everyone from infrastructure provider, like what we do here at Cerebras, all the way up to application developers and consumers is just incredible.
Now, this like demand spiral right now is like crashing into like the physical world where AI data centers are like consuming over like 1,000 terawatt hours of like electricity a year, which is like more than like 30 countries combined. And Goldman Sachs says that it's already seeing like rising household electricity bills because of it.
Mm.
So this like power availability has like replaced hardware as the number one bottleneck for building new AI infrastructure. So like in your opinion, like how does like this energy constraint reshape who's going to actually win this race?
Yeah, I think that's definitely power is one of the constraints that we have today. And there are many companies out there today that are looking for data center space. And one of the key, right, rubrics for finding a good data center space is that you have enough power available. And the other thing we're seeing, by the way, is because like more often than not, the local municipality cannot commit to providing enough power, or they cannot commit to providing it consistently. We're seing companies building their own power plants just within the data center or just adjacent to the data center. I mean, Elon Musk did something crazy. He brought up 1 gigawatt data center with his own power plant in within a year. So that's like an Elon superpower kind of a thing. But we're seeing more and more companies do that. I think there's really, it's hard to stop capitalism and human inventiveness, and I think what we'll see is it's typically when there is a lot of demand, us humans come up with crazy ideas, crazy engineering, and we solve the problem through engineering. And we've seen that happening time and time again. I think it's going to happen again. We'll figure out new ways, if it's around more efficient ways to produce power, if it's about solar, if it's about power cells, nuclear energy. I mean, there's so many different ways we can harness energy. The universe is full of energy. Just look at our neighbor, the sun. So we'll find smart ways to harness that. Short term, it's probably will take some time to ramp up that technology, but I'm fairly confident that we will solve that. I think it will also force very healthy constraints. Again, when you're doing engineering, it's really good to have constraints because it allows you to solve key problems and design the right solutions. So I think it will also push on efficiency, which, going back to our discussion earlier, efficiency is really important for AI because it's such a massive workload.
Now, I'm curious to get your thoughts on like OpenAI quietly shutting down its Sora video API this month. They were citing like unsustainable inferencing costs per generated minute. So this is really interesting to me because it kind of like states that like not every AI capability that works in like a lab is economically viable at commercial scale. So like, I guess in your opinion, can you tell us like where the real economic limits of AI inferencing are right now?
Yeah. So I think it is interesting, to your point, OpenAI's move. So that move is where they announced that they're shutting down Sora, but it's important to note, it was done as part of a bigger exercise OpenAI did of refocusing the company as part of maturing the company. Now, I'm just speaking based on what I read in news articles. That's no, inside information or anything like that, of course. But as OpenAI's continue to scale the company, and remember, they've grown very, very quickly thanks to their success with ChatGPT and AI models. But they've grown the company very quickly to thousands of employees. They reportedly, right, are planning an IPO. As part of that, they're focusing their efforts, and rather than going in too many different directions, they focus on the directions where they see, viable path to be successful as a business. And as a business, you need to make more than what you put in, right? That's like a basic rule for successful businesses, basic rule for capitalism. So I think it makes sense, for video generation, there's certainly many potential applications that can make it very successful. But also I have to remember, like, at the end of the day, one company can only focus that much. So it makes sense to list your priorities, trim things that seem valuable, but maybe not what you can focus on right now, and focus on what's going to make you more successful. Looks like OpenAI, based on what they reported, they're going to focus more on enterprise use cases. Video generation is not that critical at this point for enterprise applications. So I think that's the story there. Now, having said that, yeah, of course, video generation, video is, one really interesting modality. If you, think of it from the engineering and research perspective, it's just that the volume of data is extremely large. Typical video, you have at least 25 frames per second. Every frame contains so many data points depending on the resolution. It can be millions of pixels. Each pixel, right, is like 24 bits. So there is definitely a lot of information that you need to process very quickly. So it's a very demanding, right, computational task that obviously also kind of increases the cost of inference. especially if you compare it to text processing. Text is a very efficient representation of data, if you think about it. You can write one sentence that describes a picture, but that sentence would be orders of times smaller in terms of the volume of data compared to the image. If you think about the image as a bit data. So text is much more efficient, and it's one way to go if you want to be kind of more efficient with how you deploy your resources.
Now, the AWS CEO, Matt Garman, publicly predicted like inferencing costs were going to drop by like 10 times.
Mm-hmm.
So if this were to happen, and like say, for instance, like the SOAR problem gets solved as well, or something like that, like what entirely new categories of like, say, AI applications just suddenly become more viable that just don't exist today?
So many. I don't know even where to start describing those applications, but the basic stuff is, I think, what I described, where inference becomes cheap enough that consumers, including consumers in developing countries, can afford to run these dozens of agents to handle daily tasks, from monitoring stuff happening right in their personal lives or in school, providing bits of information even ahead of time of when you need it, identifying, think about a student, right, at school, elementary school. A couple of agents can help that student really by identifying the things he has trouble on, just by listening in on conversations in school and how they're doing homework, and then helping them with a focused effort on the areas they need more help on. Think about the elderly people, right, who maybe have cognitive decline or challenges in either hearing or seeing. Agents can actually help them by identifying the areas they need help, supporting them, keeping their loved ones informed on what's going on. There's so many possibilities, and I think, as a side note, there's all these doomsday discussions of AI and all those things, right? The Terminator scenario, which I think we should be aware of and kind of figure out how to manage. But at the same time, people overlook the massive potential positive impact, right, AI is going to have across so many different levels. And in particular, for populations that maybe we're not as fortunate as you and I to live in a Western country, Western society. So I think the potential is massive. And the cheaper inference gets, the more that positive upside is going to be available to a broader set of people. And Matt from AWS is spot on. If you look at historical trends, inference has been becoming cheaper and cheaper all the time because we are building better models, but the newer models are actually more efficient than the older ones. Now, if you compare GPT-4 to today's, GPT-5, GPT-5 today is faster and cheaper to serve than GPT-4. That's because the hardware got much better. Even if the hardware per unit became more expensive, on a per token basis, it's actually cheaper, and that's how we should think of it. And the models themselves became more efficient. So the models are better, but they're more efficient. The hardware they're on is more efficient. So that allows us to continue pushing the cost down. And I'll give you one example of such, right, efficiency optimization, which ties to AWS, which you mentioned. The other thing Matt mentioned or announced a couple of months ago is Cerebras partnership with Amazon, where we're going to match the Cerebras wafer scale engine chip, which is the world's fastest inference chip, with Amazon's Trainium chip, which is the chip they purposely built for AI, training and inference. We're marrying them together with an efficiency technique called disaggregated inference. And through that disaggregated inference, this combination of these two chips, we're going to get the world's fastest inference at a much higher throughput. So Trainium is going to handle the pre-fill phase, the prompt processing. Cerebras is going to handle the token generation. And combined, that's going to give us even more efficient tokens and cheaper tokens.
So I saw that like OpenAI's GPT 5.4, it just scored like a 83% on a benchmark, which is awesome because it's measuring how well AI performs jobs with like real economic value, where it's like matching or like beating human experts. So I guess like the bottleneck to deploying that capability at scale is no longer the model. So is inference infrastructure now like the single biggest variable determining how fast like AI actually changes industries?
Yeah, by the way, I'm really happy that you mentioned that benchmark because I think it's a bit overlooked. So, if I may, I just want to highlight that benchmark. It's called a GDP val. It's a benchmark OpenAI came up with. And I like that benchmark because it focuses on AI's ability to produce economically valuable work. That's, I think GDP may stands for GDP, but I'm not sure. But it's kind of represent economical valuable work. And so far, a lot of our benchmarks on AI have been this, MMLU, where you just answer a general knowledge question or some abstract math question or some abstract coding question. And these were good, but solving a really complex mathematical problem does not necessarily mean it's highly applicable to just general purpose, white collar, right, knowledge work. GDP-Val is exactly that. It's a benchmark that looks into common tasks that are handled by white collar knowledge workers and seeing how much can the AI handle that task effectively. And what's amazing, going back to my point about models are getting better all the time, we're hitting no wall, is if you go back to GPT 4.0, which was a very popular model at the time, considered very capable, it scored only 12% on this benchmark. It means 12% of the tasks, it was identified as doing a better job than the average human expert in the field, right? So kind of doing pretty poorly back then. Today, GPT 5.4 is part of OpenAI's announcement. They highlighted numbers. GPT 5.4 scores 83% on the very same benchmark. So majority of the task that is not, white collar knowledge worker task, GPT 5.4 is handling better than the average human expert on that specific field. So, which I think is an incredible progress. And that's exactly the benchmarks that we need to build AI that is really focused on, right, being more effective at doing economically valuable work. So, that's really cool progress. And I'm happy that we have this benchmark. Basically, 7x increase in quality in just under 2 years, I think, is, from when 4.0 was launched until 5.4. But going to your question, I think what's holding back further adoption, on one hand, yes, there's the capacity, which, like we spoke earlier, it's about producing enough silicon, deploying that silicon in real estate, data center space, and powering that data center. That's one constraint. And if you talk to many AI companies, AI startups out there, they'll tell you that they actually are having a hard time to procure the capacity that they need, the AI capacity that they need. So there is definitely a constraint there. But I think the other limiting factor is also us, humans, identifying more useful AI applications. I think we have seen a lot of success. I actually think the first killer application of deep learning was actually autonomous vehicles. And if you live in San Francisco or the Phoenix area or LA, you can actually hail a Waymo. It will come pick you up, no driver. It's pretty incredible. The other weekend, I was in Vegas with my son, and we actually took a ride in a Zoox. Also, no driver. That was very cool. I own a Tesla. I have full self-driving. It works pretty magically. That's an incredible, right, application that is running on deep learning, by the way, right? It's not language models, but it's neural nets for image recognition and segmentation and things like that. Coding assistance is another killer application that is kind of exploding in a positive way as we speak. I think I'm still blown away by what OpenAI Codex is able to do, by what Claude Code is able to do. I don't think it takes away the role of software engineer. in my company, we're still hiring a lot of software engineers, but it definitely makes them way more productive because coding, which would take a lot of their time, can now be done so quickly. And maybe I can also highlight that OpenAI is a customer of Cerebras. They use wafer scale engine to power OpenAI Codex. And if you use Codex, you have access to a model called Codex Spark that is powered by Cerebras. That's super fast. People have been loving it, and we're still doing a lot of work to power more and more of OpenAI's workloads. So definitely, audience should check out OpenAI Codex and Codex Spark. But I think there's still so many opportunities to leverage AI to have more killer applications. And again, think about, I mentioned earlier school. It's top of mind for me because I have two young kids. They're in school, and AI can help them tremendously. They already are using AI, but it's not still, the applications are not fine-tuned as much. Think about the elderly, how much AI can help them. Think about different professions. I mean, really, the sky is the limit. And I think we still need to figure out all these applications for, AI adoption to grow. So that's a separate aspect from the capacity, but still super important.
So this last month, three like frontier models dropped that like OpenAI's GPT 5.4. There was like Google Gemini 3.2, Grok's 4.20. So like the competitive gap between these labs now have like compressed down to weeks, right? So like when models are essentially like commoditized that fast, I guess like what becomes the actual differentiator for like companies that are deploying AI into production?
It's a great question. I do think in the fullness of time, the differences between the different model providers, even between open models and frontier models, are going to be extremely diminished. I mean, it's already has been happening, right, to a large degree. Although frontier models, I still feel they're ahead of the open models, but their open models are always catching up and closing the gap. I do think the differentiator is going to be in the application layer. How much did you tailor the application? Now, tailoring the application, part of it is the user interface, right? That's definitely part of it. But I think it goes way beyond that. If you understand the users really well, if you understand the use cases, you can fine tune the model much, much better. And this is already done by multiple, both open and closed labs who are fine tuning models for different use cases like coding. That's one example with, instruction fine tuning with RL and things like that. It's about aggregating the right data, indexing it correctly. It's about context engineering, right? Which is how you engineer the prompt you provide to the model so it handles this task not just correctly, but also in a way that is efficient. That's a little bit overlooked, but you can see that models supported context length have been growing, but also it's been used more and more. I think Claude Code's prompt has either leaked or they published it. I don't remember. Either way, you can see how much context engineering these guys are doing, which I think is a large degree of the magic that is Claude Code, right? So I think that's where really the secret sauce is moving to. Not that models are not important, they continue to be very important, but to your point, the differentiation is gradually diminishing. And where the new differentiation is moving to is the application, the context engineering, is the right user experience.
And then before I ask like the last question for this interview, in case the audience wants to get in touch with you to learn more, like what's the best way to get in touch with you?
I'm available on LinkedIn. I publish some stuff there, and people who are interested can read, and we can also always message me there. I'm always up to learn something new and to have an interesting conversation.
Cool. And then last question. I think 2026 is going to be the year of like AI agents. Gartner predicts like 40% of enterprise applications will have AI agents embedded by the end of this year, which is up from like less than 5% in 2025. So that's like a big like 10x jump in just 12 months. So what does the infrastructure layer actually need to look like to support that type of growth?
It's a great question. Like we said, it's super clear right now that inference is becoming the dominant AI workload, and agents is a key part of this happening. So I think we're already seeing happening on the ground is inference stacks are becoming more specialized, and compute that was pretty much monolithic so far is becoming more heterogeneous. We'll see separation in terms of the stack between prefill and decode, like I mentioned earlier, what we're doing with AWS. We'll see memory services specializing in things like prompt caching to be able to handle larger workloads faster. We see specialization in networking, caching tiers. Some of those things were also announced in GTC by Jensen, where he basically listed like 7 different chips, right, for that are part of the inference area. But it's not just the compute anymore, right? It's networking, it's storage, it's fast decode. So the system architecture is evolving to specialize around these specialized compute chips. Memory is going to be like a central battleground, both memory capacity that we need and memory bandwidth, like we discussed earlier, right? One of the advantages of the Cerebras inference is exactly that. And Cerebras, we will continue pushing on that front, and I expect others to push on that as well, just because it's such a key constraint for inference. So yeah, it's going to be more so on how to optimize the data movement, not just the compute on the data. I think models will keep on getting better at delivering economical values. Like we discussed earlier, there's new benchmarks that are coming up that focus on, okay, how do we actually make sure AI is able to improve in doing economically valuable work? That's going to continue being a massive and big trend. And that's part of enterprises adopting it. Enterprises they will adopt the models that are good at that, not just, solving mathematical problems. And the last thing is we'll have to solve the capacity challenge. And I'm very optimistic that we will solve it.
Well, thanks, Haggai, for hopping on the show. I learned so much about AI inferencing. And to the viewers listening at home, stay curious.
Thank you, Tony. It was a pleasure.